In this class, we're going to consider the chain rule for differentiation. So when you first start differentiation, you learn some of the fundamental rules, such as the power rule, the product rule, the quotient rule, maybe how to differentiate trigonometric functions. And they cover quite a wide range of function types to differentiate, but they don't cover everything. So we need to start adding a bit more kind of versatility to the types of function that we can differentiate. And one category of function that they don't cover are composite functions. And that's when we need what we're going to look at today, which is the chain rule. So the chain rule allows you to basically differentiate a bunch more functions than you could with these other rules. So technically the chain rule is for differentiating composite functions, but it's not always immediately obvious that the function that you're dealing with is a composite function. You need to think a little bit about the fact that it is a composite. But in reality, you'll recognize when to use this rule, and that can be the challenge, not using the rule, but recognizing the rule, or recognizing when to use the rule. You'll see that the formats tend to follow along a similar pattern. For example, as we'll get into the examples, you'll see a bracket with a power would be a classic example of using the chain rule. But before we get to the examples, let's just kind of backtrack and think a little bit more about the idea of differentiating a composite function. So let's say that we've got these functions here. We've got y is some function of u, and then we've got u is equal to g, some function g of x, okay? If we merge those together to make a composite, then we can say that y is f of g of x. So I've just basically taken this u function, which is g of x, and put it inside the f function. So we get y equals f of g of x. Now, there's a rule that basically tells us that if this original function y is differentiable, and if this function u is differentiable, then the composite function will also be differentiable. Okay, so that's the first important thing. Just the fact that this composite would be differentiable based on its two original functions. Then we can consider how to actually go about taking the derivative. And there's a couple of different ways you can sort of think about this, but differentiating this function here to get dy dx, so derivative of y with respect to x, in this kind of way that we've conceptualized it here, would be equal to dy du, okay, dy du, derivative of y with respect to u, times du dx. Now, this probably looks a little theoretical at this point, and it'll make more sense once we apply it to an actual example. And so this is kind of the first format. So notice that this is almost like fractions. These are kind of not fractions in the sense that they're derivatives, but notice that dy dx would be what you would get if you times these two like fractions together, because the du dx, sorry, the du on the top and the du on the bottom here would cancel, and you'd be just left with dy dx. Okay, so that's one way that we can conceptualize this. The second way we can conceptualize it is just to think of in terms of f and g, and we can say the derivative with respect to x of this composite function, which is f of g of x, like this, is going to be equal to, and this can also be a little confusing in general terms, but it's basically the derivative of this overall function, which is going to be f prime of g of x multiplied by the derivative of the internal function, which is g prime of x. That really is, in essence, how the chain rule for composite functions works. You take the derivative of the sort of overall function, and then you multiply that by the derivative of the internal function. And that's actually what this is saying as well. Because remember, y here was our overall function. The function we've got here is y. So we're saying, right, we're taking the derivative of that y function, and then we're multiplying that by the derivative of, in this case, u, which is the internal function. Because remember, this g internal function was u. That is saying the same thing, just using f and g notation instead. So it is useful for sure to learn these two forms. It is useful to think about the theory of how the chain rule works, and I would encourage you to spend time making sure that this does make sense to you. But in practice, when you start using this rule, this will kind of maybe get a little bit backgrounded, and you'll just kind of get into a bit of a flow. of knowing how the rule works and maybe kind of put this theory to one side. Okay, so what we'll do, we'll work this function here, and we'll think about it using the rule, and then we'll maybe think about it just a little bit more intuitively, and then we'll do the same with that guy over there. So using the rule on this guy would require us to sort of identify a u function, which is going to be like the internal function. And it would require us to identify the sort of two base functions, if you like, that make up your composite. So we could say here, we would need to introduce a line of working to say something like let u equal x squared plus 1. Okay, so that's basically like our internal function. The one that's inside. So notice that the two functions you've got here are this x squared plus 1 inside the bracket, that's a function, and then the overall bracket with a power on it is another function. That's like an exponential function, something with a power, so that's our outer function. So that something with the power is playing the role here of your f, and the internal function is playing the role of g. So if we've now identified u, the internal function, is x squared plus 1, then we can take the derivative, so du dx, which is going to be 2x. And then the other thing, so if you look at this version here, du dx is one of the things that we need to make our derivative. The other thing we need is dy du. Now we've defined this internal function as being u, so we could rewrite the overall function. This is these are kind of separated out pieces of working at this point. We could say, well, if that there is u, then that whole thing is just u cubed. Okay, like that. And then that allows us to take the derivative, so dy du as 3u squared. Okay, all we need to do then is to look at our rule, because we've now got this guy here, and the rule just says multiply these two things together. In other words, multiply this guy to this guy. So if we go ahead and do that, then we get dy du. So actually, let's just write it out in full. So we're going to get dy dx equals dy du times du dx. Okay, because that's what the rule says. Dy du is 3u squared. Du dx is 2x. I'll just maybe use a bracket to separate that out. Now, remember that we're trying to find the derivative with respect to x. So we should have like an x answer, basically, a bunch of x's. And it's just because now we can kind of back substitute to put the thing that we nominated to be u, x squared plus 1, back in there. So we get 3 times x squared plus 1 times 2x. You could leave it like that. Normally we would pull this, sorry, it should be a square there. Normally we would pull this term back in front to make it 3 times 2x, which will be 6x, x squared plus 1, all squared. Okay, so quite a lot of working in that, and when you start doing these initially, you'll find it maybe a little confusing to keep track of your, or maybe even to nominate your u function and things like that. But you can think of this more intuitively, and that's how I tend to teach this to students. I will definitely show everyone, like I've shown here, how to use this rule formally. But informally, all this chain rule really says is multiply the big function, the outer function, differentiate the outer function, and multiply that by the derivative of the internal function. So the overall function here is like the big bracket with a power. So if we wanted to differentiate that, let me just put it here at the side. If we wanted to differentiate that, we're kind of just using the power rule, because it's just, if you imagine that being like a giant x, so it's x cubed. Well, the power rule just says multiply by the power, and then leave your like x or whatever it is. In this case, it's the bracket x squared plus 1 alone. Take 1 off the power. And then the thing that makes it the chain rule is then multiplying by the derivative of the inside of the bracket. The derivative of the inside is 2x. So multiply this by 2x. Tidy that up by multiplying the 3 and the 2x together, and you get 6x, x squared plus 1 all squared, which is what we got down there. So you can very much like shorthand these. And in fact, at the end of this lesson today, we're going to talk about something called the general power rule, which is effectively what I've used there to rather than going through all of this work. But sometimes you do need to work through these when you get into maybe more advanced problems. So I'm going to keep emphasizing that there are shortcuts, like practical shortcuts, like what I just did there, where you could take the derivative of this using the chain rule in literally like 15 seconds, or you could take a minute or 2 minutes even to do it this long-winded way. But it is important to know how the rules work. Let's take a look at this guy. First thing with this guy here, he's not in a differentiable form because well, it would be in a differentiable form for the quotient rule, and we're not going to use the quotient rule here though. We're going to use the chain rule, and one way we can put it into a differentiable form to allow us to then use the chain rule is just to bring that bracket to the top and use our exponent rules to take that negative 2 power and turn it into a positive 2 power. So that's now roughly in this format here. Let's start this one by thinking about the derivative in that less formal, more intuitive way. So that would say just basically consider that bracket to be like one term, like an x term, is the way that I like to think of it, with a squared on it, and then use the power rule on that. Well, the power rule would say multiply your power in front, so 2 multiplies in front, there's a 5 there already, so that's going to become a 10. Leave the bracket alone, take 1 off the power, which is going to go down to a power of 1, so we won't bother putting that on. That would be the power rule. The thing that makes it then the chain rule is multiplying by the derivative of the inside of the bracket, which is just 2, using the power rule. Take one more line to times the 2 and the 10 together to get 20, bracket 2x minus 3. Now, if we then go through this more formally, we should get the same result. So let's have a go at that. So let's nominate our internal function to be u. So let u be 2x minus 3. That means that we can take du dx, the derivative of u with respect to x, which comes out to be just 2. Because we've nominated this thing here to be u, then this function is now 5u squared. So f of x can be rewritten as 5u squared, okay, like that. And then we could take our, this one's actually a little bit, I should maybe have used the other rule for this one because the function was written in terms of f rather than in terms of y. But I'll tell you what we'll do. We'll just actually put a y there. Just remember that y and f of x are kind of interchangeable. So just to keep the notation to use this version rather than this version, although they are basically saying the same thing, I'm just going to switch that up to a y. So now we can take our dy du, which is just using the power rule. 2 times 5 is 10, u reduce the power by 1, so it goes down to a power of 1. Now we just need to use basically this little format here, which would say that dy dx equals dy du, derivative of y with respect to u, times du dx. Now dy du is just 10u. Okay, dy dx is the one that we took earlier, which was 2. So it's going to be this guy times 2, which is 20u. But we know that u was nominated to be this thing here. So that's just 20 times 2x minus 3. And if we compare, the intuitive version that we did initially was this guy here. This more formal method is this guy here. Obviously, they've come out to be the same thing, which is what they should be. It might be, though, that your calculus course that you're taking in school or in college or your teacher may necessitate that you use this more formal method. But if not, then you can use this more intuitive method. Ideally, of course, like a lot of these rules, you should know both. This would be the sort of the mathematician's way of doing it, the formal way, and this is a little bit shortcutted. So I mentioned in there that there's a sort of general power rule. I mean, you're going to see the chain rule in a whole bunch of different formats, and in fact, because there's so many formats and we've only really covered essentially one format here, like a bracket with a power, I've added another video after this one just to work through some examples where the chain rule is presented and applied to different formats. But a lot of them will be in this format, and we can apply here what we could call sort of a general power rule. So if you have your original function y equal to some function of, well, let's call it some function u of x to the power of n, then what the chain rule is telling us is that if we want to take our derivative, so dy dx, where you've basically got a bracket with a power and an internal function, which is what we had here. And this has got its own special name because this is so often the format that you use the chain rule in. But basically here we would apply the power rule. This is just exactly what I've done here, but more formalized. So we would apply the power rule to bring the n in front, leave the internal sort of function the same, take one off the power. So just using the power rule, but then multiplying this by the derivative of the inside of the bracket. The inside of this is u dash x, or du dx if you prefer to write it like that. So let's just call it u dash x, or it could be du dx. So that's just basically a formula, if you like, that formalizes exactly what we did here, but in the shorthanded way. That's effectively the rule that we use to get these shorthanded results. So have a think about that as well. So it is a little confusing in the sense that you've got different notations to use the chain rule. This is really just dependent upon whether you're using y or f and g. And then you've got this kind of special version of the chain rule, which is actually, again, just saying exactly the same thing. It's a derivative of the overall function multiplied by the derivative of the internal function, but applied to a particular case, which is where you've got some function in a bracket to a power, which is just a really common presentation of the chain rule. Chain rule is super important. It comes up in a whole bunch of different techniques. It's really, really key for your calculus, differential calculus going forward. So please do spend some time trying to get your head around the theory and a couple of examples that I've worked there. And if you're cool with these, then maybe scoot into the additional video in this class just to check me out working a few additional examples, because sometimes, although the theory is important, it's not until you actually see different example types being worked that you kind of get a feel for what the rule is really saying. And all this rule is really saying is to use the power rule twice. And you'll see that as you start to work more examples. So like a lot of rules, it seems complicated in theory. In practice, maybe not quite so difficult. So I hope that makes sense. And when you're ready, just check out those examples in the next video.